you're going to get again, again a three-dimensional space. Okay? Now here is the interesting thing. What if I take a line now and I, take a cross product of the circle actually. S1.
Assigning each point S1.
So S1 is circle. So it's a collection of all those points x, y, z, z, x squared plus y squared. Huh? It's going to be a cylinder. It's going to be a cylinder because what you are doing, so you are taking a point and to each point you are assigning, a circle. So you put them together, you get a cylinder out of it. So cross product is an amazing thing. It's an amazing thing. Think about it. Added pair there, क्या कितनी मजे की चीज है. Think about it. Okay? So we take up each point and then. But you can also think from this perspective. So S1 cross R.
Assigning each circle a point.
So take a circle and attach a line to each point of the circle. So what are you going to get?
Again cylinder.
Slender. Slender ही मिलेगा.
Point को circle दे तो भी cylinder, circle को point दे तो भी cylinder. मतलब ये reverse है.
This looks interesting.
दोनों साइड से ओपन होगा.
कैसा होगा?
दोनों साइड से ओपन होगा.
क्या ओपन होगा?
ऊपर वाला ऐसा भी, नीचे वाला ऐसा भी.
किसका? Cylinder. Yes, it's going to be an infinite cylinder. Now here is the question. Take a circle and take its cross product with. So what would be S1 cross S1?
Circle को circle दे.
Okay, so you're going to take a circle and attach a circle to each point of it, but orthogonally. So all these lines are orthogonal. Okay, so take a point and attach each point a circle. So take this point, attach a circle. Take the point, attach a circle. Take a point, attach a circle. So what are you going to get?
सर एक गोल पाइप बन जाएगा पता नहीं क्या ट्यूब
बन जाएगा.
किताब में पिक्चर देखो. You're going to get a torus actually. That would be donut actually. Isn't it?
Donut.
That would be donut. So a tube. ठीक है? तो गाड़ी के अंदर ट्यूब डालता है. That tube, you're going to get a tube actually. ठीक है? So you can understand a torus as cross product of circles actually. So there are a number of ways you can understand all this. And now you can ask an interesting kind of question. Think about it. You can ask an interesting kind of question. So instead of, curves, say I'm taking R cross, some curve, that curve looks like this actually. What would be the meaning of that? Yeah, R cross a curve that looks like this actually. Oh, not R, but say S1. S1 cross this kind of a curve. Circle? So you take a circle and to each point you assign such kind of a curve. So क्या बनेगा?
सर ये कुछ पानी के ये होते हैं मोटर उनके अंदर ये कुछ
सुराही बन जाएगी. सुराही. That would be a surai. Picture. So it will be a kind of a picture.
Sir, it seems somewhat like the solid revolution or other. We take one step and then we are copying them. So we get something.
Not copying them, but to each point you are assigning the curve. Okay? Anyway, so that would be a topic in pathology. Anyway. So the torus, so there are a number of ways to understand torus, and so what we just saw that you took a circle and you are taking another circle that you are putting orthogonally and you are putting into the motion, so it's going to swap out what you call the torus actually. Okay? So keeping in view this notion, try to make sense of the parametrization of the torus actually. You will see that it talks about two circles and one circle being moving along what do you call the circle. Okay? So for the example of the torus, go through this stuff. Okay. नॉर्मल वेक्टर तो आज डिफाइन करना शुरू ही लेट गए सर यहाँ नॉर्मल वेक्टर डिफाइन करेंगे ज़्यादा से आपको पता है ठीक है then we can start surface integrals now let's our surfaces let's have a kind of a different look to our surfaces. So imagine I have, that's the domain, that's U in R2. That's the domain of U in R2. But I know that R2 can be seen as this actually. In it. R2 can be seen as this, so that's really R2. Or you have this domain of the function defined in this R2 actually. So this R2, this domain of R2, what you're calling it U, is going to consist of these such kind of lines actually. Are you getting the point? Okay. And obviously if it is containing lines, so it's going to contain all these patches as well. Now I want to see, I know that P is doing what? P is a parameterization that is taking everything from U and sending it into R3 and creating a surface. Okay? But that was a local definition. What do you mean by local definition? So this is the point-to-point definition. So the P takes a point, okay, and throws it into R3 actually. But now I want to do, and what I want to ask, imagine what if I take a line actually, so because all these lines and all these regions are also part of the domain, so these lines will also be transformed onto or what do you call not shifted, but transformed onto, mapped onto the surface actually. Okay? So what are you going to have? Something like that. So you take, for example, a point. So this point is mapped onto a point on surface. But this point really, for example, say lies on the intersection of two lines actually. So this line will be mapped onto a line onto the surface, okay? And this line will be mapped onto, what do you call, a curved line onto the surface, okay? So this mash of the lines is going to become what? Really curved lines. Okay? This mash of the curve is going to become such lines actually. So I want to formalize this idea. So this is an intuition. So I want to formalize this. I want to write it mathematically, more precisely and carefully. Okay? So what I would like to write, so the next thing that I would like to do is that imagine you have a P, that is defined over U and throws things in R3 and it parameterizes a surface S. Okay, so in other words, S is the image of this parameterization. And now I'm saying that take a point in U. So let's take a point in U. So whatever story I told you, I'm just going to write it mathematically, the same thing. So take a point in U and define a path or a line that passes through this, this point actually. Okay. And we assume that you have this XY axis sitting here actually. So X and Y axis. Okay. So I have a line that passes through this point A. Okay. along x-axis. So what would be the equation of this line? Can we find a parameterization of this line? So let's call this gamma of t. So what would be the equation of this line actually? That passes through the point A and goes in the direction of x-axis. So कैसे लिखूँ? You're going to say, okay, it should pass through A, okay, and plus t, but what is the direction in which I am going actually? Back and forth on this line, if I am moving on this line. So it's going to be which direction? X-axis direction. Let's denote this by E1 actually. Okay, so that E1 is the direction actually.
Unit vector on the x-axis.
Unit vector standard unit vector. Okay, so let's call E1 to be say 1, 0. Is it making sense? So I hope we are happy with this kind of parameterization of line that passes through point P and has a particular direction. Okay, TE1. So what would be the line of such? For example, let's call this as delta of t. So the delta of t is going to be a plus t e2. Okay, a plus t e2. Why you have a plus t e1 here, and a plus t e2? How does this represents the line actually? So it represents the line. Think about it. So if I take a point here, any point on this line, okay, so I can reach to this point by doing what? Let's move from A and some distance, some magnitude
along
t
E1.
along E1.
along x-axis.
Okay. So in other words, A plus T1 is really A1 plus T and A2. So I'm just moving some units along x-axis.
T units, sir. We
T units.
can you say T units?
Okay, T units along x-axis. So this intuition is important. Otherwise, you're going to say, "Kya likh rahe hain?" ठीक है जी. So now, what would be this line? So if this line is say gamma of t, and this line is delta of t, and everything is mapped under P onto this surface, so what will happen to these lines? So first of all, the A will be mapped onto the surface, so maybe you're going to get P of A somewhere here in R3. So here you are in R3, okay. By the way, E1 and E2 can be also treated as the UV directions. You can also have XY direction, but you can also call them UV directions as well, because everything we are writing in the terms of U and V. And we are reserving X, Y, Z for the R3. एक ही बात है. XY कहें, UV कहें, this doesn't make any difference. So what do you think? How can I get this point? So you just have to operate P onto it, so this is P of A.
Parameterization.
P of A. So how can I get this line? So if I apply, so if I apply P onto this entire line that falls in the domain of it, so what will happen? So you're going to get a line that passes through the point. So this curve is really,
P of A.
so what should I call it? P composition gamma of the T. So it's a P composition gamma of the T is, I'm going to call it, this is U coordinate line on surface. U coordinate line, okay, on S. And how about the other line? That will also be mapped. So how are you going to map? So just compose it with P. So P is going to send everything. So P composition delta of T is really the V coordinate line. Okay. So I relate. Okay, good. Now, at this point, so you can also treat these directions, these lines, as these lines are the principal lines here. In other words, every point on the in this region can be expressed through these lines actually. So I can reach here by moving some units horizontally and some units vertically to it. So similarly, you can express everything on this surface using these two lines actually. Okay, decomposition. So therefore, you call such kind of surface as a two-dimensional object. So it's a two-dimensional object actually, sitting in three dimensions. Okay. So in other words, so you want to move on Earth. Okay, you want to say what is your precise location on Earth. You only need longitude and latitude. So surface of Earth is a two-dimensional object. Okay, but it's sitting in three dimensions. That's a different thing actually. Ambient dimension. We have about cubing. Okay, so you can have one thing that has a lesser dimension sitting in a higher dimension. So the outer space is three dimension. But in three-dimensional space, you have this two-dimensional object. So why I'm calling the sphere as a two-dimensional object? Or why I'm calling this surface as a two-dimensional object? Because think about it. So if I want to reach somewhere here, so I can say, okay, and I'm here actually. So I can move some units along, u coordinates and some units along v coordinates, and I can reach it. So I only need two quantities to describe everything on the surface. So it's really a two-dimensional kind of a surface. Okay, so that's one of the things. So let's take a point and let's compute, for example, a tangent vector along this principal u principal direction. And I can also compute the tangent vector along this v principal direction. Okay. The question is, what would be that tangent vector? So how you can compute the tangent vector here? So what you can do is that you take p composition gamma. So let me write it here. So I'm just finishing. Okay. I know the guys are okay. So let's p composition gamma. So I want to draw a tangent vector on p composition gamma. So what do I need to do? So take p composition gamma, compute prime and substitute 0. That's really the tangent vector is. Like for example, for the path, p prime of 0 is really the tangent vector. So what would be p prime of gamma? So the p prime of gamma can also be seen as that this is the derivative with respect to time of p of gamma of 0. So what is gamma of 0? So if you compute it, gamma of t and then substitute. If t equal to 0, बाद में substitute करना. First you need to compute it. So what are you going to get? P of gamma of t, so I'm going to say a plus t t1. Okay? Write this here, so it's going to be t equal to 0. So this is same as this actually. But do you remember, when you see this, do you remember something?
Directional derivative.
So that's a directional derivative, or the partial derivative. Because this is E1 is a principal direction actually, so it's a partial derivative. Partial derivative with respect to what?
P. U.
U actually, because E1 is representing the principal direction of the U. So this is the partial derivative of P with respect to U at the point. So when you're going to substitute t equal to 0, what will happen?
So we'll get A. Yeah.
So that's really partial derivative. So this guy that has an interesting importance when you were, for example, looking at it, PU cross PV. Remember, ठीक है, जिसके through हमने surface define किया था. Okay. Now this PU has a special meaning now. So if you compute PU at, this is same as that you compute the PU at the point A. So the PU at the point A is representing the partial derivative of the U of the parameterization P at point A in the direction of the U actually. And similarly, you can also show that P composition gamma prime of 0 is going to be PV of A. Okay. Now, what would be So keeping in view this, what would be the interpretation of now PU cross PV? So PU cross PV. So that condition actually that defines a surface. So your P is going to define the surface if the PU cross PV at all points of the domain must be non-zero. Non-zero or zero? Non-zero होना चाहिए. Non-zero होना चाहिए. Okay? So what would be the meaning of it? How are you going to interpret it? So now I know that PU and PV are tangent vectors. Okay? They are tangent vectors. So if they are tangent vectors, these two tangent vectors must be linearly independent of each other. Okay? They must be linearly independent of each other. Anyway, there are many ways in which you can interpret it. The last thing that I would like to have. So in other words, if you have been given a parameterization and a point on the surface and you want to find tangent vector, just compute the partial derivatives. That is going to be the partial derivative. Okay. So why I am taking all this pain to coherently define this theory, so that when I for example say you that this is really a tangent vector, okay, which is giving you the change in the principal direction, you should not just take my things on my words, but you can literally see that it all makes sense coherently. Okay. Important beta, we should go through the theory. The last thing, the really last thing. Okay. Not a big calculation. Now I want to say, imagine you have this surface. Okay. And I take a point on it. Then I know that on this surface I can draw, these two tangent vectors in the principal direction, PU cross PV. So that's PU cross PV actually. Okay, so PU cross PV. I'm not writing it. How can I find the equation of the tangent plane to that point? So imagine I'm interested in finding the equation of a tangent plane at this point actually. So how can I find it? What should be the way to say, what should be the trick? What kind of points this plane is going to contain, which is going to be tangent at this point? Okay, here's the thing. So here's a picture. So if this is a point and this is PU and this is PV, so where is going to be the PU cross PV? So it's going to pop out of the surface actually. Yes. The PU cross PV actually. Okay. So if these two vectors are tangent vectors, we will eventually call this PU cross PV, a normal vector. So that will be really a normal vector. Okay. Not defining it today normal vector properly. The question is, what should be the relationship of the points on the plane with this PU, PV or PU cross PV? क्या relationship होना चाहिए? Orthogonality होनी चाहिए. So if you want to, for example, that's a good point. Here's the thing. Okay. So if I have this point, this point की description क्या होगी? So what will be the description of this point? So this point is going to be really P of A. Okay. This point has coordinates P of A because it's an output of a point, A in domain actually. And on this plane I'm taking an arbitrary point, say X. Okay? Arbitrary point X. So how can I say that this X really lie on the tangent plane actually? Okay? How can I say it?
इनके लिए स्पैन हो रहा होगा.
So the way to say this. So consider the difference vector of these 2 points. Okay? So the X minus P. Okay? X minus, we should say P of A actually. what should be the relationship of x minus PA with PU and PV, or the cross product of PU and PV? So it must be orthogonal. Okay, so the PU cross PV is going to be an orthogonal vector. So I have a vector here, okay, that really passes through both points. Okay, and I will just kind of represent the difference of x and P of A, and I have this PU cross PV. So if this x is really lying on the tangent plane, then these two vectors must be orthogonal. These two vectors must be orthogonal. Can you see it? Why? Think about it. So you have x minus P of A, so the P of A is, this vector, and you take the x minus P of A, so take this vector, and then you are saying that this would be, a tangent plane if this vector is orthogonal to PU cross PV. Why? Think about it. Because if you have a plane and you have a normal vector, okay, onto this, what do you call, plane, and you take any tangent vector, that tangent vector, or any vector that lies in the plane is going to be orthogonal to this normal vector actually. अगर आप एक vector दे दें, so here's the thing, okay? Simple thing. So this normal vector, PU cross PV, okay? And I'm taking a vector in 2 dimension, that's 2 dimension actually, okay? So I'm taking it. So what should be the relationship? So any vector that lies in the plane
is orthogonal to that.
so it's always going to be orthogonal to this PU cross PV. No matter where you vector put, जहाँ भी put करेंगे. So what would be the relationship between this, PU cross PV with, a vector that lies in, what do you call, the plane. So you're going to say it's going to be orthogonal. And you can say other way around as well. हर वो vector जो कि इस vector से, every vector that is orthogonal to this vector is going to lie on the plane actually. ये भी तो है ना? You can go other way around and think other way around as well. Okay, हर वो vector that is orthogonal to this vector, at the point is going to be is going to sit in the what do you call tangent plane. So that's precisely what we are saying. So you are saying that okay, you take x minus PA, so that if this vector will be in tangent plane if its dot product with PU cross PV is 0. So that's the equation of the tangent plane. That's going to be the equation of tangent plane on surface. Okay? You have to keep in view that x is an arbitrary point of the plane. You can take any other point, take difference, and it should be orthogonal to, what do you call this, PU cross PV. So you can find through this formula very easily the equation of the tangent plane. Okay? So what information you need? You need PU and PV obviously at A. So everything is, you're talking from the point of view of the point A. So compute this vector. You already know the point A. Take your arbitrary point. So x is like really x, y, z, could be anything. So x is an arbitrary vector containing say x, y, z. Okay? Take difference, take dot product of it and equate it to 0. Whatever linear equation comes as an outcome is going to be the equation of the tangent plane. So tangent vectors and tangent plane, when them are.
ये जो यहाँ पर पूरी प्लेन